Hello everyone, and welcome back to Reverse Engineering Linux 32-bit applications. In this video, we're going to talk a little bit about assembly. Now, we've said before that if you have the time and if you're really interested in the stuff, it wouldn't be a bad idea to take a little detour and go through the assembly and shell coding class here at Pentester Academy. But if you don't have the time, or maybe you're not expecting to get that deep into assembly, I'm going to give you just the very basic bits that you need in order to be able to do reverse engineering. So if I am reverse engineering an application, I need to understand three things, three players, if you will, into the situation. And the first are registers. So we said before that a register is a high-speed memory area. So we have high-speed memory areas that are built onto the CPU chip. These allow us to do things very quickly. As soon as we get off of that chip, things slow down a lot. So modern processors have a lot of these registers available. For our purposes, we want to look primarily at three registers. We have one that's called the EAX. The E in all of these cases stands for extended. We're talking about 32-bit stuff, and that is an improvement or an extension, if you will, of 16-bit assembly. So if you look at the original IBM PC, it had an 8086 processor, which was a 16-bit chip. Later, when we got things such as a 386 chip, we had 32 bits, and with the Pentium chips and beyond, we have 64-bit chips. So if I have a register that was called AX originally, the 32-bit version is called EAX. This register, the A register, is often called the accumulator, and this is the most used register. It is used for a lot of things like scratch values and return values from functions and things like that. Incidentally, if I look at just AX, I can further break that down into AH, the high byte, and AL, the low byte. So it's all the same register, no matter how you refer to it as EAX, AX, AH, or AL. So I can get the subparts out of that register if I so choose. Two other registers that are very important to us. One of them is ESP, the extended stack pointer. We talked about the stack briefly before. We said that this is an area in memory where many things are stored and many things are passed back and forth on the stack. So ESP points to the start of the stack. Also recall that we said the stack grows downward. And EBP is used often to store the previous value of the stack pointer. So whenever I call a function, what will happen is a bunch of information is put onto the stack. So the stack is expanded downward in memory. My new values are added to it. And when my function returns, those values are removed from the stack. So a stack, speaking of things that we need to understand, is what we call a last in, first out construct. So the last thing that was put on the stack is the first thing to be removed from the stack. So when we put something on the stack, we say we push it on the stack and we pop it off of the stack. So you can think of it kind of like an inbox that might be on your desk. You put papers on the top. Those are pushed onto the top of the stack. And then when you remove them, we pop them off the top of the stack. So every time I call a function, we put multiple things on the stack, and we'll see exactly what these things are in a little bit. And often we will say that we've put a frame buffer on the stack. So we have put a certain number of known values onto the stack that are grouped together, and they all go away when a function returns. We also have to understand calling conventions. So calling conventions are nothing more than a protocol that is used to pass things to and from functions. Now, for us at this juncture, we're just going to look at the default calling convention. There are some other calling conventions that are available, but we're going to look at the most common default situation. So let's go ahead and get started. And we're going to build a very simple application. Now, unlike the situation that you're going to run into with Windows, most likely you already have a compiler installed. When we built Evan's Debugger, we installed a package called Build Essential, and that package would include certain things such as a compiler. So first, let me go ahead and edit a program. So I'm going to edit a C file, and I've called it bufferoverflow.c. I'm going to use gedit for our purposes today. I could use a nice integrated development environment. I could haul out something like Eclipse, which those of you who are serious programmers might be familiar with, but we really don't need to do all of that for our purposes here. For our purposes here, it's just as easy to edit a simple program and then use something like GCC on the command line to compile it. So this is going to be a C program. So I will start by including two things, standard io.h and standard lib.h. Those are two libraries that pretty much every C program is going to need. I will define a function that returns an integer. I will call it function, and it will take a single string as a parameter. I will define a couple of local variables. I will define a local string, and this will contain the value of conjunction function. It's kind of a shout out to Schoolhouse Rock, which was something that they used to have on TV a long time ago. So if you grew up in the US and you're old enough, you might remember that they had these little short things during commercials. And probably one of the better known ones was the little guy singing conjunction junction, what's your function? This is the function for the conjunction function. All right, I will also define an integer, call it local int. I will give it the hex value DEAD BEEF, dead beef. I will define a second string, local string 2, and I will give it 10 bytes of storage. This is enough for 9 characters plus the terminating null byte. And what will this function do? Not much. It's going to call stir copy that will allow me to copy a string to another location. So I will copy the parameter that's passed in to local string 2. Now this function actually has the destination listed first, followed by the source. Once that's done, I will return a value. I will return a value of 1. Every program has to have a main function. So I'll go ahead and write a main function. It also returns an integer. It takes 2 parameters, an integer argc and argument count, how many command line arguments were passed in. And then it takes an array of strings as the second parameter. Once again, I will define some local variables. String, which I will set equal to main function. I'll define an integer, local int, and this one will be hex 11223344. I will call function with arg v1, the first command line argument that was passed, and I will return 0. So every program is going to have a return value, and a return value of 0 means success, and any other return value means failure of some sort. Okay, so let me save that. So it's been saved. Now what? Now I need to build it.